With the problem framed, it's time to meet the data. And to make a decision that trips up more projects than any modeling choice, deciding what good means. Before we train anything. Quick recap. For each applicant we predict the probability they'll default. And the two mistakes cost different amounts. A missed default costs $5,000, a false alarm just $1,000. Keep that in mind. Here's what we know about each applicant. 7 numeric facts: age, income, years, employed, credit score, loan amount, and how many loans they already carry. And 2 categorical ones: their housing situation, and the purpose of the loan. Numbers and categories behave differently, and that will matter when we build the pipeline. And here's the one column we want to predict: default. Repaid is 0, defaulted is 1. 500 rows, each already labeled. That's what makes this supervised learning. Notice the classes are lopsided: 23% defaulted, 77% repaid. That imbalance is exactly why plain accuracy is out. A model that blindly predicts repaid scores 77%. And helps no one. So we need a better scoreboard. What single number actually tells us a model is good at this job? Start with recall. Of all the applicants who really defaulted, what fraction did the model catch? Here, a plain logistic model at the usual cutoff catches 39 of the 115 defaulters, a recall of just 34%. Only a third. That's low, and we'll raise it later by tuning the threshold. High recall means few missed defaults, and missed defaults are where the money leaks. Precision asks the opposite question. Of all the loans the model flagged as risky, how many really would default? 39 right out of 57 flagged, precision of 68%. High precision means few false alarms, and fewer good customers turned away. Here's the catch: you can't max both at once. Where you set the decision threshold trades one for the other. Flag more applicants and you catch more defaults, recall rises, but you also raise false alarms, so precision falls. Loosen or tighten the cutoff, and they seesaw. So which do we favor? The bank speaks in money. Expected cost equals missed defaults times 5,000, plus false alarms times 1,000. That's the number we ultimately minimize. Recall and precision are just how we steer toward it. But there's a wrinkle. Recall, precision, and cost all depend on the threshold. To compare whole models fairly, we'd like one score that doesn't care where the cutoff sits. That score is ROC AUC. The idea is simple. A good model should rank defaulters as riskier than repayers. Here are 10 applicants placed by the model's risk score. A good model pushes the red defaulters to the right. To measure it, take every possible pair of one defaulter and one repayer. Check. Did the model give the defaulter the higher score? Each pair it orders correctly is a point in its favor. The AUC is just the fraction of those pairs the model gets right. Our logistic model scores 0.8. Half would be a coin flip. 1 would be a perfect ranking. 0.8 means it's a genuinely good judge of risk. So here's our definition of success, set before we train. Select the model by ROC AUC, who ranks risk best. Then tune the threshold to minimize expected cost. And always report recall and precision, so the trade-off stays visible. Finally, the numbers to beat. Random ranking scores an AUC of 0.5. Approving everyone costs $575,000. Beat both, or the model isn't worth shipping. To recap, know your columns, numeric versus categorical, and the target. On imbalance data, accuracy is out. Recall and precision trade-off, and cost is the real goal. Select models by AUC, then tune the threshold. Next, we roll up our sleeves and explore the data.